Hi, I'm Amir Hossein Mirzabozorg, and in this video, I want to talk about Comprehensive Abaqus Package Chapter 14, DFLUX Subroutine and Thermomechanical Analysis. How to ask your video-related questions. Don't hesitate to ask any questions you might have about the explanations presented in this video using the comments below. We will try to answer all questions regarding the video details in the comments below. New Abaqus users who want to develop their modeling skills faster in their projects can request user-oriented online and offline services. Subsequently, we offer step-by-step guidance, tutoring, and consultancy regarding their problems. The online service includes online sessions, and the offline service includes creating special tutorials. In addition, a combination of the two can be requested. This is the table of content for Chapter 14. Let me talk about this one. This is the mechanical solution. Mechanical solution and thermal solution. In the semi-coupled thermomechanical analysis, thermal solution is dependent from mechanical solution. But mechanical solution is dependent on the thermal solution. So first, we solve this one, then import its results for the mechanical solution, then solve the mechanical solution. In the other case, we have mechanical solution and we have thermal solution. It is for semi-coupled and this is for fully in the fully coupled case, both the solutions are solved simultaneously. Okay, it's like this. There is no first one and second one. Both of them are solved simultaneously. And in the semi-coupled or semi-coupled case, this one can only be done using Abaqus standard. Okay, Abaqus standard, but this one can be done using both of them. Can be done using both of them. both the standard and explicit. Okay. And for example, we have a pipe like this, okay? And for example, here hot water or hot fluid passes the pipe, and also some of it like here. And to analyze this model, you can do it as a semi-coupled analysis. Semi-coupled. And it gives you good results. We will not have any problem. There is no need to solve it as a fully coupled case. Why? Because we have a small plastic strains. But when you have large plastic strains, like what we have in metal forming processes, like hot rolling or hot extrusion, then it must be solved as a fully coupled analysis, because due to large plastic strains, the plastic work is changed to heat, and then we have a lot of body heat sources, and then the mechanical solution is affected by thermal solution. Also, the thermal solution is affected by mechanical solution. This is our example. It's based on this paper. Computer analysis of thermal phenomena and deformation in lap joint welded by a laser beam. I want to solve this problem. This is a lap joint. It is fixed from both sides, and laser passes here and it creates weld. And I want to solve it. Here we have moving heat flux, moving heat source. It's laser beam. And this is the finite element mesh. And also here you can see the moving heat source. And it is the temperature change along the thickness. And you can see the stress contours and other things. Okay, here also I want to show you another paper. It is about laser forming. we apply laser to a plate and then it bends. Bending happen. It's very interesting. One side is fixed and one side is free. And then you apply laser here, laser moves here, but not for one path. For example, for a lot of passes. For example, 15 passes, 30 passes, 100 passes, and then the plate will bend. It will goes up. It will goes up. It's very interesting. We do this analysis using semi-coupled procedure. Also, you can do it with fully coupled procedure. But in this class, I told you I don't talk about fully coupled case. I only talk about semi-coupled case. And I will solve it using semi-coupled case. Also, this one, they have done it using semi-coupled procedure. And okay, I go back to the okay. It must be heat transfer. Sorry again. And here you can see the mesh. As the laser moves in this region, here I made a smaller elements. And also the origin is very important when you want to define moving heat flux. So I transfer it to here, and also yes, it's good. In the interaction, notice that when the laser moves, for example, these regions are welded to each other, but these regions are not. So, and I must write the subroutine. Why? Because here I have set it to user defined. It means that I want to use subroutine. Here it says user subroutine DFLUX must be attached to the analysis job. Okay, we must write the DFLUX subroutine and attach it. Very good. So here we have the documentation. I go to the Abaqus user subroutine reference guide. Here we have DFLUX subroutine. Now I want to talk about DFLUX subroutine. It is one of the famous subroutines of Abaqus, and it has a lot of usage in 3D printing, in welding simulation, and like that. Okay, overview. User subroutine DFLUX can be used to define a non-uniform distributed flux as a function of position, time, temperature, element number, integration point number, etc. in a heat transfer or mass diffusion analysis. This is the interface of the subroutine. Each subroutine has its own interface. When you want to write a subroutine, you must copy the subroutine interface, create a text file, copy it in the text file, and file save as, set it to all files. I name it dflux.4. 4 is the type of Fortran file. .f and .4. I myself, I always use .4. I have not used .f. I don't know what is its usage. And finally, I delete it. And then I open it again. Okay, here I think I must, yes, I think this is correct. It must goes to column, it must goes to column 7, I think. Some of the interfaces have problem. And I must delete here, and I must write my code. Subroutine, as I told you previously, it is function in Fortran. Each function has some inputs and some outputs. And outputs are the variables to be defined. Flux 1. I want to write the subroutine. Here we have the constants of the subroutine. Here we have the constants. Okay. And we have the equation here. I must write it in Abaqus. First, I must define the inputs. Okay. I define them as double precision. Double precision means that you will have 12 decimal places, and so we have good accuracy. Double precision, Q, eta, pi number. R0 S V, yes, we have pi here. What is Q? It is 1500. Also, you must write it like this because it is double precision. Eta is 0, oh, sorry, it is 0.75. 0.75. R0, it is the laser spot radius. Okay, we have laser spot. Its radius is 0.001 meter. And S is the penetration depth. It is 4 millimeter. Okay, this is Q2. Exponential of okay. And what is R? We must also define R. R is the distance between the center of the laser spot and each point in the region which I selected for applying heat source. So I must also define R, X, and Y, and Z. Okay, also Z. Oh, sorry, I think, yes, also I must define Z, but R is, R is X in the power root of X in the power of 2 plus Y in the power of 2. Yes, it's for the surface. It's for the surface. Okay, it's for the surface. And yeah. So X is quartz 1. This simulation is completed, the thermal analysis. If you see the moving heat flux or moving heat source starts from one side and then it goes to the other side. And you can see the profile of the temperature along the thickness. And if you see the orange color, or let me increase the number of colors, even this laser is powerful enough to melt this region, okay, this region, because you can see the temperature of this region. It will be melted, and then it will be melted and we will have the welding. That's it. It is the temperature field. Now I want to do the mechanical analysis by using the result of the thermal analysis. I go to the part module. I create a copy from model 1. I name it model 2. I go to the property, but I always use compatible mesh. And I create another job. And I run it, let me check everything. Yes, I think it's okay. And I run job 2. Now Abaqus reads the temperature field from job 1 and calculates thermal strains and apply it to the simulation. So they are thermal loads, and then you can see the stress and strain. If I show you thermal strain, delta epsilon thermal is equal to minus alpha delta T or delta theta. Okay, and because when the temperature is increasing, then thermal strain causes compression. So this minus is because of that. And delta L thermal is equal to minus L0 alpha delta theta, delta T or delta theta. Both of them are correct. And also mechanical strain plus thermal strain is equal to total strain. And this one is calculated from the mechanical relations, and this one is calculated from here, and also it can be calculated. If you see, it's doing the simulation. Oh, sorry. I didn't define. Sorry, I didn't define boundary conditions. Sorry. Here we must define fixed boundary conditions. Sorry. Oh. They are fixed here. They are fixed, and now it is correct. The stress will be induced into the simulation. why there is no, aha, sorry, it is not solved because every 10 increment, yes, every 10 increment, sorry, after 10 increments we will have the result. It's 6. No output. They are closed. These regions are closed. Why? Because of the deformations. Okay, because of the deformations. The deformations causes that here we have tie constraint. Okay, here we have tie constraint, and in this region we have contact. First they are closed, by after it because of the deflections we don't have contact anymore. Okay, in these regions it's due to the deformations. And also you can see the thermal stresses. You can see the thermal stresses. It takes a lot of time to be completed. After the class, I will run this model again to get the appropriate result, and I will show you the result for the next session. Only I will wait for two other frames. And then I will end the simulation. And it is moving. And if we check the PQ values, you can see that they are small PQ values. They determine that our simulation is correct to be semi-coupled or not. Did you understand? If they are less than 0.1 through the analysis, 0.1 means 10%. Less than 0.1, as far as I remember, it is acceptable to be semi-coupled. But if it is more than 0.1, then it is not very acceptable. And you can see that it is working, and I will wait for another increment again and another frame again, and then I will kill the simulation to see what happens. And also, what should I tell you next? I think I have mentioned everything. Then we can go to the vibration analysis. I mean chapter 15. These unsuccessful attempts, most of them are due to contact. Also, some of them are due to the thermal loads and the large deformations. I think during the analysis it remains less than 0.1. I will run the model completely and show you in the next session. See a status. And you can see that these closed parts are due to the large deformations. Due to the thermal deformations, we have these contacts here. And even you can see that you can see this deformation. You can see this deformation. This deformation, it is real. It is real deformation. It's due to the thermal strains. It's due to the thermal strains. Okay, I kill this simulation, and in the next session I will show you the final result, and also I will discuss it. So I kill it, I save these models, and I run it after the class to see what will happen. Okay, so now we go to the next chapter, which is the vibration analysis. How to purchase packages or individual chapters. Each of the packages and individual chapters includes CAE, JNL, and IMP files, step-by-step tutorials with detailed explanations and investigation of the results, slides and reference papers and standards. Packages specifications and payment details are provided in the video description. Also, you can pay the cost of the packages in 2, 3, or 4 installments according to your budget or income. In the future, updates will be provided for free for everybody who purchases each chapter or each package. The cost of each chapter or package will increase after each update for new buyers, but those who purchase the package would have endless access to all the upcoming updates. This will make the content up to date for new needs and new problems which must be solved via FE simulation. You can contact us using Telegram or WhatsApp, or you can send email to us. We can have one-on-one tutoring on the AnyDesk WhatsApp, and we can make special tutorials to your order. We can conduct high-quality simulations for your thesis, exercises, and industrial projects. And we offer support in writing the modeling and result discussion part of your thesis. And we have consulting services for MSc, PhD positions or job interviews. And finally, we can help you to prepare the presentation of your simulation works. Now I want to suggest you several related videos of our YouTube channel. Thank you so much for watching this video. Have a good time. Goodbye.